Okay, so sorry about that. I like I had to send out a quick message and stuff to my previous class because like right at the end when I was answering some of their homework questions, I cut out my internet cut out and it had been cut out for like 10 minutes uh I had to restart my router, but thankfully that fixed it and everything's good now. So, um I get the new Call of Duty. No, I don't play Call of Duty games. So only FPS games I play are arena shooters because I'm a true old man. Um, okay, so all we need to do really to be done with Chapter 6 is to finish up our discussion of least square solutions. What that means is being able to actually do uh, one of the least squares problems, that is, given some system or some equation ax equals b, to find a least square solutions for it. And so the idea here uh, is we went through this whole explanation last time for the conceptual reason why we can do this. I mean, we actually proved what the normal equations did. But these normal equations are the key to finding least square solutions. And so this theorem that I added a bunch of stars to here says the set of least square solutions to ax equals b coincides with the non-empty set of solutions to the normal equations a transpose a times x hat is equal to a transpose b. So if we find a solution to the normal equations, that is a least square solution to the equation ax equals b. So this tells us exactly what we need to do to solve a least squares problem. You will get a feel for why this is so important if you take the course Math 401. Math 401 is it's a course that's basically just a long list of um, applications of linear algebra in various contexts. So it is pretty nice to see things like Google PageRank, various. I mean, if you look at the notes, so Justin wrote the notes for the class that everybody uses when they teach Math 401, and the if you look at the notes, like if you look at just like the chapter headings, there's a whole list of a ton of topics. I think it was Justin wrote a lot of. I know uh, someone else, I can't remember off the top of my head. Someone else actually wrote a big chunk of the notes too. It wasn't just Justin. I guess someone else helped with that. I don't want to not give credit to people, but I can't remember off the top of my head. Anyway, um, so what is the deal with least squares? Maybe we should just do one good example to show how this works. So let's say find a least square solution to ax equals b, where A is the matrix. Let's make it a big one. So let's say let's make it a 6 by 4 matrix. So we'll say 1 1 1 1 1 1 1 1 0 0 0 0 0 0 1 1 0 0 and 0 0 0 0 1 1. Okay, and let B be the vector -3, -1, 0, 2, 5, 1. Okay, and so what do we compute? So we would compute A transpose A. I'm not actually going to write that all out because that's a really big matrix. I'm just going to write out what I get out of this. So I'm going to write out A transpose A. It turns out this is 6, 2, 2, 2. Down the first column, same thing. And then it fills out in the following way. Interesting. Okay. right. So there's my A transpose A. What do I also need to compute? So what is it that we're doing, right? We're trying to write out the normal equations here. So recall, normal equations are these, right? A transpose A x is equal to A transpose B. Okay, and so someone asked in chat, will you tell us, someone else asked if Livermore was the person who helped write the notes. That's differential equations you're thinking of. Uses Livermore's notes. So it's Math 401 uses Justin's notes, but I know someone else helped him compile them, especially recently. I think the last few chapters, like the last 5 chapters, were written by someone else. I just can't remember who it was. Someone else asked, on the exam, will you tell us if we need to use least squares for a matrix or do we need to figure it out for ourselves? I could phrase the question differently. I could say, find a vector that minimizes this distance, right? So yeah, I wouldn't have to state it as find the least squares solution. I could say find a vector that minimizes this distance, right? And then you know that the least squares solution is the one that does that. Yeah, okay. The video-related questions I'll answer at the end. Okay, so anyway, so let's see here. So maybe I should write my normal equations here so that you get what it is I'm looking at. I want to solve this thing, right? We could actually check whether or not this is consistent. It's not, so ax equals b is not consistent, so this thing actually doesn't have a solution, but this thing is going to be guaranteed to have a solution, okay? It's a good exercise for you to think about why this thing is guaranteed to have a solution like this. My hint to you, and you can pause the video here, is last time we went through this whole conceptual demonstration of what the normal equations do and what x hat is, right? And our idea was this. So this was the first page of it. I'm not going to go over all of that, but this is something you can pause the video here. And then the last page of these calculations was this. Now, hidden in that calculation, even though I didn't say it explicitly at the time, I might have said it, is the fact that there's a proof hidden in those computations. It's like a one-line thing. You can say for y, this always has a solution. So this always has a solution. This is always consistent. Okay. Even if ax equals b is not, the normal equations are always. Okay. Now, here's A transpose A. If you don't believe me, I will show you the computation here in a second. What does A transpose B look like? Well, it turns out A transpose B is, so let's see, A is a 6 by 4, so A transpose is a 4 by 6. B is a 6 entry vector. It's in R6, so then the result should be a vector in R4. So this is 4 minus 4 to 6. Okay, there's A transpose B. Now again, if you don't believe what's going on here, here's actually the computation for those things so that I don't have to write them out. So there they are. Right, there's the things written out if you really want to see them in that way. Okay. And so now I get something that is not so bad here. The normal equations aren't so bad. So there's my two matrices. Maybe I'll leave them on the screen. Yeah, there we go. All right, and so using those two matrices and my normal equations here, what is the augmented matrix for the normal equation? So augmented matrix for A transpose A x hat is equal to A transpose B. What is this? So this is 6, 2, 2, 2. Well, okay, I'm just going to write it out. No reason to know why I'm rattling off numbers there. So here's the vector that's on the right-hand side. I'm jamming in the last column. So this is 2, 2, 0, 0, minus 4. So we're reading row-wise here. 2, 0, 2, 0, 2. And then lastly, 2, 0, 0, 2, 6. Okay, so there's my augmented matrix. This thing can be row reduced. You can use your imagination here. We've done enough row reductions that we're allowed to do this. So again, reading row-wise, this is 1, 0, 0, 1, 3. Oh, I already, okay. 1, 0, 0, 1, 3, 0, 1, 0, minus 1, minus 5. 0, 0, 1, minus 1, minus 2. And then 0, 0, 0, 0. Okay, last row is entirely zeros. Is that T or I? I'm writing, everywhere I'm writing T's. These are the transpose. This is the transpose symbol. Okay. All right. And so, what do I get from this? So this is row equivalent to my augmented matrix here. So this gives me, if I write the associated equations here, so this is x sub 1 plus x sub 4 is equal to 3. And x sub 2 minus x sub 4 is equal to minus 5. And x sub 3 minus x sub 4 is equal to minus 2. Right, and then the last thing gives me nothing. X sub 4 is equal to x sub 4. Right. Okay. And so what do I get here, right? My general solution is x hat, which is my constant vector 3 minus 5 minus 2 is 0. So parametric vector form is our friend, as always. Plus x sub 4 times the vector of things multiplying at 1 minus 1 minus 1. 1. Right. Okay. Oh, actually, no, wait. This should be flipped. So these are the pluses, and this is minus. So scratch that. This is no good. Let's rewrite this vector. All right, this is what happens when you cut corners, right? So the x sub 1 is, here, we'll write this out like this. So this is 3 minus x sub 4, and x sub 2 is minus 5 plus x sub 4, and x sub 3 is minus 2 plus x sub 4, and then x sub 4 is free, it's equal to itself. There we go. So minus 1, 1, 1, 1. Yeah. Okay, now we're right. Okay. All right, so there's my general solution. So there's a choice here. And so you might say, wait, but my least square solution is supposed to be my minimizing, my distance minimizing thing. How could there be infinitely many of these? That happens, right? Typically, if you're asked to find a least square solution, you just care, right, that you find one. You don't care if there's more than one, but it is interesting and it is useful to know when there is in fact exactly one, when there is a unique least square solution. All right, this gives you an example showing that there's not always a unique one. Right, there's infinitely many here. I have a choice, right? Of course, this augmented matrix could be whatever. Well, I could ask you, what kind of restrictions are on this. It's a more conceptual question, but anyway, the point is that this is something that happens. It's not always unique, but it is interesting to know when it is unique. Okay, and so that is answered by the following theorem that helps you to say something about that. So let A be an m by n matrix, then TFAE, the following are equivalent. Right, it's been a little bit since we've used that. So first thing is the equation AX equals b has a unique least squares solution. Okay, so it has a unique least squares solution for each b in Rn, or Rm, sorry. So that is equivalent to the columns of A being linearly independent. Now you're going to stop here. You're going to say, wait a minute. The columns of A are linearly independent. And why aren't we just done, right? Forget about least square solutions. Why columns of, so columns of A are linearly independent, then, well, then A has an inverse, right? Its determinant's non-zero. A has an inverse. Multiplied by its inverse, that gives us our unique solution. What's the problem with that? Well, A is rectangular, right? So that's the problem with that. If A is square and has linearly independent columns, well, then you're good to go, right? Screw least square solutions. You can just find a unique actual solution to the equation. If we have a rectangular matrix, however, and the columns of A are linearly independent, that is equivalent to this equation having a unique least square solution for every choice of right-hand side vector. And this itself is equivalent to the matrix A transpose A being invertible. Yeah, so Gustav had mentioned, like, for instance, if you're thinking about this as distance minimizing, then yeah, I mean, it's not strange that when you consider, say, the set of, points that are some fixed distance away from, some other point, or the set of points that are some fixed distance away from some other object, it's not impossible to imagine situations where there are more than one such point. So he comes up with the example of a sphere. So that's of course something you can think about. But I mean, there's many ways in which that can in which this can happen in terms of distance. So you don't have to worry about that too much. Okay, so these three things are equivalent. All right. Now, of course, this is the thing that you want to be true. So then this is the statement that you're going for, and to show that this is true, you use one of these facts. Okay, and that does it. Okay, so when these are true, of course, if a single one of these is true, then all of them are. So when these are true, then the least squares solution, the least squares solution, x hat to ax equals b is given by x hat is equal to A transpose A inverse times A transpose B. This is not an amazing thing. I literally just took the normal equations and multiplied both sides by A transpose A inverse. Okay. All right. So a quick definition, textbook mentions it late, and I don't think I gave a name to it before, but this quantity ax hat minus b, this minimum distance thing, this is sometimes referred to in the literature as least squares error. Okay. Which totally makes sense. Conceptually, this is exactly the amount you miss being a real solution, right? This is how close you are to being a real solution, right? So how close x hat comes, that looks bad, close, how close x hat comes to being an actual solution. To ax equals b. Right, this is what that distance is measuring, right, literally. And so this is the obstruction, right, this positive number is the obstruction to x hat being a real solution. Right? It's how far off you are. Okay, now we went through this business of the QR decomposition for a reason, and it's that when you have a QR factorization, least squares stuff becomes real easy. So the next theorem shows how nice a QR factorization can be. It's not the only reason it's nice, but it is a reason. So how nice a QR factorization can be. So the following theorem says, given an m by n matrix A, with A having linearly independent columns. So we're in the case of the previous theorem. Now we know that AX equals B has a unique least square solution for every B. Okay, let A equal QR be a QR factorization of A. So remember, Q has orthonormal columns, and R is upper triangular with positive entries on the diagonal. Okay, and so it's a square matrix. So let A equals QR be QR factorization of A. Then for each B in Rm, the equation AX equals B has the unique least squares solution given by X hat, which is R inverse Q transpose times B. Which is a lot less nasty than what we had written before. Right. All right. Okay. Yeah, and so someone mentioned in the chat what is the main application of least squares. So this is fitting to a least squares line. It is. I'm not going to. I debated whether or not to do this versus going immediately to chapter 7. If I do the application of least squares stuff, it won't be until after I finish chapter 7, even though this is actually included right in the next section. Just because I want to get to, I want to get through the stuff that I do in chapter 7 first. But I may go back to this. And when we go back to this, I'll show how. So they mentioned it looks like you're only solving for the slope of the line that you're fitting to. You're not. You're solving for you're doing the whole line, and I can go over how that is, but not. It's not going to be on your exam, and I'm not going to do it until later, until I've done some of the chapter 7 stuff. So anyway, but yeah, no, that's interesting. That's an interesting way to think about it. And if you want to think about that in a way, you can actually just go ahead and read the next section. This is section 6.6 in the textbook. So there's a way to deal with this fitting to an arbitrary line, not just one that say passes through the origin. You can fit to whatever line using this method. You can actually fit to other curves too. You don't have to just fit to a line. You can fit to whatever curve you want to. This is something, if you're really interested to see various more in-depth examples of curve fitting and line fitting, then Math 401 is a nice place. Or a statistics course, of course, will probably do more of it than Math 401 would. But anyway, so yeah, so we will talk about that, but it won't be till later. Okay, so that is it for chapter 6. That's all I wanted to say. So when we start up again, we will be in chapter 7. We will cover symmetric matrices, quadratic forms, and I may talk a little bit about optimization. Other than that, we're going to have kind of some freedom to talk about a range of topics. So one of the things, like I said, I can mention least square fitting, curve fitting, stuff like that. And then what I had made kind of a habit of doing when I had time at the end of semesters was mentioning on like the last day of class or maybe the day before something like the Hadamard matrix conjecture, which is just a funny, still open problem concerning Hadamard matrices, which you can look up if you're interested, but I'll define them in that class. So anyway, we have some time left in lecture. We have, since I started late, we have say like 20. Looks like 23-ish minutes looking at my timer. So if you have any questions about the material, then you can feel free to ask them. And if not, then you can take off, but I will be here for the next 15 minutes regardless. And then I'll post your exam. I have some office hours for another class. Immediately following this, I'll post your exam, I don't know, in like another, say, 2.5, 3 hours. What is the purpose of row space? Well, so you saw when we first introduced it that it does, in a way, behaves differently, right, on its face than the column space, even though it is a column space. Of course, it's a column space of A transpose, right, not A. So the row space of A behaves differently. When I say differently, I'm talking about in terms like mechanically. If I ask you to find this, the process that you go through to find the column space of A versus the row space of A it's different, right? The best way that I can explain the difference, say, between columns and rows, right? Like what is the difference between writing vectors as columns and vectors as rows? And is there any important distinction? Yes. I mean, the distinction, of course, so whether you chose to write vectors as rows or columns ultimately doesn't matter. Even considered in the same space, and the reason why that has to do with something that we're not going to talk about, unfortunately, in this class. I mean, I could bring it up later, but it doesn't really fit into the material in a normal way, is the notion of the dual of a vector space. So here, I'll do it on a different sheet. So if you have a vector space, there's a notion of what's called V star, and this is the dual vector space to V. I'm not really going to get into what that is, but it's defined as it's set of linear functionals on V. I'm not going to get into what that is, but the point is there's this object called the dual vector space to V. One interpretation of one example of this duality is the switch between rows and columns. Okay, so you will hear, if you read the literature on this stuff, you'll hear statements like, rows are dual to columns, like they're the dual object to columns. And what that means is that there is a map. For instance, there's an example of a map that goes, say, from V to V star that takes a column, right, X, Y, Z, and writes it as a row, X, Y, Z, written as a row like this. Okay. There's a map that does this, and this map is an isomorphism. This is an isomorphism. So you understand the language of isomorphisms, and so you know that what that means when you write down two things. So it turns out the dual space is a vector space. That's why I wrote dual vector space, because given a vector space, the dual space is always also a vector space. And it turns out that it's isomorphic to the vector space you started with. So V star and V are isomorphic. So they, as vector spaces, they behave exactly identically. So now it's a question of whether you want to argue, is it the same to use columns or rows? Well, it's the same in the vector space sense, right? There is an isomorphism that goes between them. Vector space computations here and vector space computations here have a correspondence, right? Now, are they equal? Not really, right? They're isomorphic, right? They correspond under an isomorphism. That's what you can say. Now, the question is, why would you want to do this? Conceptually, there's a nice thing, or there's a lot of nice stuff that pops out of these considerations. So one is that vector spaces and their duals, and not just vector spaces, but more general spaces and their duals can be paired. Okay, what's called, say, the vector covector pairing. So if this is a vector, this is a covector. Okay. And so there is the vector covector pairing, which if you're doing, column row deal is really, it's really a swap, right? It's XYZ going to XYZ. But what does that? Right? Well, the transpose, right? And so an example of vector covector pairing would be the pairing of the row XYZ with the column ABC, right? Okay. So how do we treat this? We treat this as a pairing. We'll call this vector V star, and we'll call this vector V. So really we have paired V star with V, right? That's what this pairing is. But what is this pairing? It's actually a dot product, right? And so the vector covector pairing is an example of an inner product or dot product. Now, again, you're going to say okay, I know what the dot product is. I don't need to write it like this. The reason why this is nice is because this also holds true for more general spaces. So stuff that is crazier and harder to get your hands on, this is still true. The resulting pairing is not the dot product. It's an inner product in general. An inner product is a thing that has the same properties the dot product has, but it's not necessarily the normal old dot product. But it's something that generalizes the dot product. So that's the reason. Okay. Let me see if I got to all the questions. Do I play Valorant? I never liked Counter-Strike since I remember I was 14. It was like 1999. And I was playing Counter-Strike and I loaded it up and I was like, this is stupid because, I have to wait and watch some idiots that I don't know play badly while I'm sitting here waiting to respawn. I wanted to play. I play all my FPS 1v1. I don't like team-based shooters. I don't want to rely on other Stupid people. Thoughts on Sekiro? When I bought it and I played it a little bit, but I put like hundreds of hours into Souls games, so I wasn't feeling it at the time. So I still need to go back and play it. But I mean, I liked what I played of it. I didn't like the fact that it didn't really have, loot. That was kind of annoying. I had the same problem with Bloodborne. I didn't like the fact that it didn't have that much loot. But any other questions? I think that covers is hitting the gamer questions because I didn't see any. Did I get everything? I think I covered all these questions. So anything else? I'm here for another, I don't know, we'll say I'm here for another, let's see, stream has been going for 40 minutes, it says 41 minutes, so I'm here for another good 15 minutes. Yeah, Gustavo. So, topics on the exam. So it's going to rely on knowledge from the whole semester, but mostly the main, it will focus on stuff since the last exam. So stuff mostly concerning, because before the last exam we had finished most of chapter 4. There was only like 1 or 2 sections left that we didn't, so it will be like the tail end of chapter 4 stuff, not very much, and then chapter 5 and chapter 6 stuff, which is every thing that we did up to finishing with least squares solution. So obviously Gram-Schmidt, like there's 100% going to be a Gram-Schmidt question on there. And of course it might not be phrased as use Gram-Schmidt to do blah. It might be phrased as, find an orthonormal basis for some subspace, right? Okay, so yeah, I mean, it's going to focus on stuff, from the end of chapter 4 to through all the way through chapter 6, but again, you're going to need to know stuff from throughout the semester. A little confused about the equation x hat equals, so yeah, the way that we came to that was the normal equations. So the normal equations are A transpose A, x hat is A transpose B. The assumption we were working under is we had those 3 equivalent conditions. So 3 equivalent conditions were, we're looking for, this is the thing we want. So we want to know when this equation has a uniquely square solution for every vector B in the right hand side. And the answer to that is, this entirely has to do with properties of A. So the columns of A being linearly independent, that is something that guarantees that. It's also something that is guaranteed by A transpose A being invertible. The second A transpose A is invertible, what does that mean? Well, if A transpose A is invertible, well, it has an inverse. So I can multiply both sides of this by it, right? So A transpose A inverse times A transpose A x hat, and that's equal to A transpose A inverse times A transpose B. But associating this in the right way, right? If I have A transpose A inverse times A transpose A, well, then I get the identity. So this is x hat is A transpose A inverse A transpose B. So that's what I did. If you really don't like doing it that way, right? I mean, right, if you have a matrix X, right, X inverse times X, that's always the identity. It doesn't matter whether the matrix is actually a product of 10 matrices or not. This is always true. But even if you didn't want to recognize that, you could do this just being careful. So, yeah, let's just look here. So A transpose A inverse times A transpose A. Well, A transpose A inverse, how does that work? So when you invert a product, it reverses the order, right? So this is equal to A inverse and A transpose inverse times A transpose A. All right, so A transpose inverse times A transpose, that's the identity. So this is A inverse times the identity times A, but this is A inverse A, but that's the identity. All right, so that's it. Okay. Did we start chapter 7 today or no? No, I didn't. Chapter 7 starts with symmetric matrices. Symmetric matrices and goes to the main statement that we want to work out in chapter 7 is the spectral theorem, which we won't get to until I'll start on chapter 7 on Monday. And then after break I'll do a few lectures on chapter 7 and that's it. I'm only going to do 7.1 and 7.2, I think. Apart from that, I'll be done. Did I like Skyrim? No. I didn't like it. It's too generic. Level scaling, loot is randomized, and scaled to your level. I mean, Elder Scrolls 5 was bad. Oblivion, Elder Scrolls 4 was okay. Elder Scrolls 3 was amazing. It's one of the best games ever made. Morrowind is one of the best games ever made. Combat in it's absolute garbage, but combat's not that important in an RPG. Exams due Wednesday at midnight, right? I don't know what I said about the due date. I might yeah, I mean I don't know. It'll either be due Wednesday or Monday. You're gonna have plenty of time to do it. It's actually gonna be shorter than your last exam. So I might make it due on Monday just because that meshes well. That way TAs don't have to worry about what they can and can't answer on Tuesday. That way during discussion they can answer any questions you had. So yeah, maybe I'll make it due on Monday. But like I said, don't worry too much about that. It's gonna be shorter than your last exam. Quick question about MATLAB project. It's fine to name the matrices with different letters from what's in the question. Yeah, that's fine. Yeah, that's fine. Yeah, that's fine. Just making sure. I mean, any confusion that could arise there, just you can alleviate that by your comments, right? When you publish the PDF of your project. I guess I didn't go over. I didn't mention that much, but yeah, I'll remind you all, I suppose, that you should publish it as PDF if I didn't say that already, because it makes it look a lot nicer. Definitely do not send like a raw M file. I'll send out an announcement about that, reminding everybody. Yeah, I could, Gustavo, I could add a little inset somewhere on the screen, for my camera next time or sometime during a lecture, but it would I'd have to remember not to write, I think I tend not to write in like the upper left-hand corner, so maybe I'll put it in the upper left-hand corner. Uh, Oh yeah, I mean I can. So I'll toy around with it because I'm teaching a history of math class next semester anyway, which I was gonna have my camera on for. So I'll uh, I'll do something like that. I'll see about putting it on for one lecture or something. Yekta, you want to see what I look like? Yeah, I mean, so that's what I was saying. I'll put the I'll put it on. Uh, I'll put the camera on some lecture. Um, maybe on Monday I'll put the camera on or something. Otherwise, what do I have? I don't even have a picture. Do I have a picture of myself? I don't have pictures of myself. I have old student IDs from like a million years ago. Oh man. Yeah, here's a student ID from like 20 years ago. This was me 20 years ago. It was more like, I guess it was more like 16 years ago. But yeah. That's a good one. It was taken at some university. It was taken at some orientation section. It was absolutely horrible. It made me regret. I was like regretting my decision to go to college. The orientation was so bad, but then it turned out it wasn't actually nearly as bad as the orientation made it seem. Uh, they forced us to watch this like play that it was like a version of Friends for college, and I mean I hated Friends, so it was pretty horrible. It was pretty much the worst weekend ever. Thought, like I said, I thought I was really in for disaster, but I don't like Friends. It was the Friends was the inferior '90s sitcom. Seinfeld was that was can't watch both. You gotta pick one or the other. I have three cats. Three cats. There. I would get them, but they're all sleeping right now. Okay. So I have to prepare for my I have to get my office hours set up for the next class, and so I think that's it. So I will see you all on Monday. I'll post your exam here in maybe like 2 hours. I'll post obviously I'll post an announcement once it's up. So be looking for it. And then like I said, you'll have at least till Monday, till Monday at midnight to do it. Anyway, All right, so I will see you all on Monday. You all have a good day too.